and welcome to another lesson on rate of reaction. In this video, I'll be comparing the zero order, first order and second order of reaction for a single reactant system, that is A converted to B. Let's begin by defining what is a zero order reaction, first order and a second order reaction. A zero order reaction is a reaction where rate is independent of the reactant concentration. For first order, it is the reaction in which the rate depends on the concentration of reactant raised to the first power. And finally, for second order, it's a reaction in which the rate depends on the concentration of reactant raised to the second power. Now let's write a rate law or rate equation for this. For zero order, it would be rate equivalent to rate constant multiplied by the concentration of reactant, which in this case A, raised to the power of 0. For first order, it would be rate equals to the rate constant multiplied by the concentration of A raised to the power of 1. Finally, for second order, it would be rate equivalent to K multiplied by concentration of A raised to the power of 2. Next, let's see what would happen if we double the concentration of A. So let's start by writing rate 1 will be K multiplied by A to the power of 0, and rate 2, which is a reaction whereby the concentration of A is doubled, can be written as this. Since anything to the power of 0 is equivalent to 1, therefore, rate 1 will be equivalent to rate 2. Thus, for zero order reaction, doubling the concentration of reactant has no effect on the reaction rate. Next, let's move on to first order reaction. Doubling the concentration would give us rate equivalent to K multiplied by twice the concentration of A. Rearrange the second equation to match the first equation. As you can see, K multiplied by concentration of A is actually equivalent to rate 1. Therefore, rate 2 equals to 2 times rate 1. So here we can conclude that if we double the concentration of A, the rate of reaction would also double. Finally, to the second order of reaction, so the first rate would be K multiplied by A to the power of 2. Doubling the concentration of reactant would give us an equation that looks like this. Rearranging equation 2 to match the first equation would be as shown. As you can see, the part that I'm highlighting in red equals to rate 1. Therefore, rate 2 equals to 4 times rate 1. So the conclusion is, for a second order reaction, if we double the concentration of reactant, the rate would increase 4 times. Next, let's move on to the rate constant unit. For a zero order reaction, the units would be rate, that would be molar per second equals to K. Concentration has got a unit of molar raised to the power of 0. Therefore, K has got a unit of molar per second. Or sometimes units like mole per dm cube per second is also used. Next, for first order, the units would be rate, which is molar per second equals to K multiplied by the unit for concentration, which is molar, raised to the power of 1. Since molar can be cancelled on the left and right, the unit for rate constant for first order reaction would be per time. Next, for second order reaction, it would be molar per second again for rate equals to K multiplied by concentration squared. Cancelling the common molarity unit would give us the unit for rate constant to be per molar per second. Knowing the units for rate constant is one way to determine order of reaction. Therefore, make sure to remember that for zero order reaction, the unit of rate constant is molar per second. For first order reaction, the unit for rate constant would be per second or per time. And finally, for second order reaction, the rate constant unit would be per molar per second. Next, let's move on to a graph of rate law. The graph of rate law is obtained by plotting rate of reaction against concentration. Since in a zero order reaction, the rate is independent of concentration, therefore we would obtain a straight line parallel to the x-axis, whereby rate equals to K. Next, for first order reaction, since rate equals to K multiplied by the concentration of A, you can see that it matches y equals to mx. Therefore, a linear graph passing through 0 is obtained whereby m, the gradient, equals to K. As for the second order reaction, rate equals to K multiplied by concentration of A squared, and this matches with the equation y equals to mx squared. And you have an exponential graph when you plot rate against concentration. Now let's move on to another set of equation for the order of reaction. It is known as the integrated rate law equation. You are not required to know the derivation for these equations. However, you have to by heart them. So for zero order reaction, it would be concentration of A naught minus concentration of A equivalent to Kt. A naught is the initial concentration, whereas A is the concentration at a given time t. Next, for first order reaction, it would be ln of initial concentration minus ln concentration equals to Kt. And as for second order, it would be 1 over concentration of A minus 1 over initial concentration of A equivalent to Kt. Next, in order to obtain the graph of integrated rate law, we will be rearranging these equations to match y equals to mx plus c. So for zero order, it would be concentration of A equivalent to negative Kt plus initial concentration, and this matches y equals to mx plus c, whereby when we plot a graph of concentration A against time, the y-intercept would be the initial concentration of A and the gradient would be negative K. Next, for first order reaction, it would be ln concentration of A equals to negative Kt plus ln of initial concentration of A. And this would match with y equals to mx plus c. Therefore, plotting ln concentration of A against time would give us the y-intercept of ln A naught and a gradient whereby again it would be negative K. Finally, for second order, it would be 1 over concentration of A equals to Kt plus 1 over initial concentration of A plotting 1 over concentration of A against time would give us the y-intercept of 1 over concentration of A and a positive gradient with value k. The final comparison between zero order, first order and second order reaction would be on half-life. So what is this half-life? Half-life is the time taken for the concentration of a reactant to decrease half of its initial value. And the symbol used for this would be T-half. Translating this definition into an equation would give us at T-half, the concentration of A would be half of the initial concentration as shown. So using this condition, we will be transforming the integrated rate law equation into an equation that gives us the half-life equation. Let's begin with zero order. The integrated rate law equation for zero order again would be the initial concentration of A minus the concentration of A at a given time equals to kT. Now we will be defining that the time is the half-life. Therefore, the concentration of A would be half of initial concentration. Using this definition, let's substitute correspondingly into the integrated rate law equation. That would give us initial concentration minus half of initial concentration equals to K multiplied by half-life. Simplifying this equation is as shown. Finally, the half-life equation for zero order would be T-half equivalent to initial concentration divided by 2K. Next, let's do the same for first order. Again, start out by writing the integrated rate law that would be ln initial concentration of A minus ln concentration of A equals to KT. Again, I would like to emphasize the conditions for half-life, whereby T would be T-half and concentration of A now is half of initial concentration. Substituting in the corresponding symbol would give us an equation that looks like this. You must recall from mathematics that ln A0 minus ln A can be represented as a division. Now simplifying this equation would result in the half-life equation of first order, which is T-half equals to ln 2 over K. Finally, to the second order reaction, whereby 1 over concentration of A minus 1 over initial concentration would give us KT. And again, don't forget to define the conditions for half-life, whereby T would be T-half and the concentration of A is now half of initial concentration. Rewrite the integrated rate law equation for second order using the conditions stated. Simplify the equation. And there you have it, the half-life equation for second order to be 1 over K multiplied by initial concentration of A. Apart from determining the order of reaction from the unit of rate constant as well as the linearity in the integrated rate law graph, we can also determine the order of reaction from the half-life graph. So the half-life graph would be a graph of concentration of reactant against time. For the zero-order reaction, concentration against time graph would be a linear graph with a negative gradient. Now let's say the initial concentration is given to be 1. Therefore, the first half-life would be from concentration 1 reduced to concentration of 0.5, because by definition half-life is the time taken for the concentration of reactant to be half of its initial concentration. Now I'm going to use dotted lines to mark the time taken for this change, and this would be the first half-life. Next, reducing the concentration of 0.5 to half of itself, which would be 0.25, would give us the second half-life. From here, you can see that the length of half-life is decreasing. This is valid because, as we can see from the half-life equation, half-life is directly proportional to initial concentration. Therefore, when the initial concentration is decreasing, half-life also decreases. Next, let's go on to the first order reaction. Decreasing the concentration of 1.0 to 0.5 would give us the first half-life, and decreasing the concentration from 0.5 to 0.25 would give us the second half-life. Here you can see that the half-life is constant. This is valid as the half-life equation for first order was T half equals to ln 2 over K. Ln 2 over K is a constant value, therefore the half-life is constant. We can also say this as the half-life is independent of the initial concentration. Finally, to the second order reaction. Again, I'm using an initial concentration of 1. Reduction of 1 to 0.5 would give us the first half-life, and from 0.5 to 0.25 would give us the second half-life. It should be visible that the half-life is actually increasing. This matches with the half-life equation whereby half-life is inversely proportional to the initial concentration. Thus, as the initial concentration decreases, the half-life increases. Before I end my video, I would like you to remember that decomposition of radioactive materials is a first order reaction. That's all for this lesson. Thank you so much for watching.